Imagine a spinning disc, and this disc has a projectile on top of it. Let's say we wanted to hit that cat. We could accurately calculate when to drop or let go of the ball to hit it every single time. And that is exactly what this video is about. This video is only showcasing and explaining the math. I won't be making this contraption in this video, maybe in the future. So like if you want to see me making this in real life. The first step is to actually find the coordinates to the target. And this is probably the easiest step in this entire video. If we have any type of distance sensor on top of a servo motor, it's basically a radar. And to picture this, you can look at this illustration, and it will actually stop once it finds the target, and we then know the angle to the target and the distance. You can also see that AD is the same as the y-axis, and BD is the x, and AB is the hypotenuse. We can then easily calculate the length of x and y using trigonometry. We have now found the coordinates to the target, and we are officially finished with step 1. Step 2 is to figure out when to let go of the projectile, and to be honest, I haven't really figured out a great solution. There are probably many better ways to solve this problem, but here is my way of doing it. This is a circle, and this is the equation of a circle. If you do not understand fx, maybe one day you'll understand why. I'm sorry for that terrible joke, but to understand this next step, you must acknowledge that y is the same as fx. And this is how we get the function for half a circle. Feel free to pause the video to analyze. This is one half of the circle, and this is the other half. The reason it's only half a circle is because the square root does not account for plus minus square root. Just like this example, x has 2 answers. In this video, I will be only looking at the positive side. We now find the derivative of fx, which is this mess. I also forgot to mention that I swapped the radius to 1 instead of r. To actually find out when to drop the object, we find out where on the x-axis to let go of the projectile. As you can see, the trajectory of the projectile is not the same as the hypotenuse. The trajectory is actually a tangent line. Using the derivative, we can actually find tangent lines. How do we know what x value to put in? We don't. That's the short answer, and that is why we use something called brute force, which is basically trying until we get the right answer. First, we try finding the tangent line when x equals to very close to the edge of the circle, which is r, because that's the radius. But we can't actually put a tangent line on the very end, because when we try finding the slope, we end up by dividing by 0, which is illegal. And that is why we do x equals minus r plus 1 divided by a big number, because then we get very close to the line, but not quite. We then do the same thing for the other side of the circle, but this time x equals r minus 1 divided by a big number. We then make a tangent line in the middle as well, which is on x equals 0. We now should have 3 tangent lines, looking like this, where this is the first tangent line we calculated, this is the second, and this is the third. We now find which 2 lines this target is in between. To make this easier to explain, I will give each line a different name. To figure out which 2 lines the target is located in between, we find out what their y value is at the target's x coordinates. This is actually way easier than it sounds like. We just put this number in here and get a output. We then do it for all of the lines, and these numbers are not accurate. I'm just too lazy to actually calculate the real values. We can now use a Python program to tell us which 2 lines this target is in between by comparing the y values. You can see that this y value is in between these 2 y values, so the target must be in between these 2 lines. We then repeat the entire process, And to find this middle tangent line, we use this formula. You basically repeat this process until you find a tangent line which has the same y value as the y coordinate to the target. You are now done with step 2, which is probably the hardest step in this entire video. Step 3, how do you know if the projectile is on the correct x coordinate when releasing it? Let's say you're releasing the projectile on minus 0.4. The easiest way to know if my projectile is there is by having a sensor there, but I can't have a sensor for every single point. Therefore, I will use another servo motor with a stick, and the stick has the same length as the radius of the circle. The stick can now rotate freely all around the circle while it has a sensor on its tip, like a Hall effect sensor. Therefore, the projectile has to be magnetic so we can sense it. But how do we know what angle to put the servo motor at so that the Hall effect sensor is at the correct x coordinates? Here, A is the same as the radius, A equals r, and C is the x coordinates from where we need to actually let go of the projectile, which we calculated in the last step. And we can find the angle for the servo motor using this formula. And that is pretty much all of the math I've done for this project. Hopefully it wasn't too boring. In my next video I might make this in real life, but I also need to calculate how many rotations per minute that this needs to actually reach the target. Please like and subscribe.